morphisms. I had introduced polynomial maps. Y, so where x and y are some fine algebraic sets, and polynomial map means that the coordinates are given by polynomials. With the FE. So just you put coordinates of these points in X into the Fi, and this gives you coordinates image point. So that's very simple. Now we will want to also consider more generally morphisms between quasi-affine varieties, so open subsets in affine varieties. And we also want to look at the projective and quasi-projective case. And that's somehow not enough to work with polynomials or elements in the coordinate rings. One needs to use rational functions to define morphisms and study them. And so I want to introduce these regular and rational functions. Will be functions which you could either say are given as quotients of polynomials, or they are given as quotients of elements in the coordinate ring. So let's look first again at the affine or quasi-affine case. So we let X be an affine variety, so X in AN is a closed subvariety. So recall we have the coordinate ring. This was just, I could denote it AX. This was defined to be the quotient of the polynomial ring divided by the ideal of X, and one could identify this with the polynomial functions on X. And as I have assumed that X is a variety that is irreducible, it means that IX is a prime ideal. So therefore, AX is an integral domain. We have seen that for an integral domain, you can form the field of fractions. So the fraction field which is just, I denoted Kx, field of fractions of Ax. I already defined that. Is called the field of rational functions on X. An element in Kx is called a rational function. Rational function on X. So now we have to see in what sense they are functions. They will be functions which are not necessarily defined everywhere on X, but on an open subset of X. So just if X is quasi-affine, so if U subset X is open and not empty, just write KU. Find this to be Kx. So for an open subset, the field of rational functions is the same. Now, as I said, elements in Kx define functions on open subsets of X. So let me find this. Basically, quotient f divided by g in Q of Ax will be defined at a point P in X if I can write this as f divided by g such that the denominator is not 0 at P. So let X local ring of X at P is just, so I denote it like this, and this is defined to be the set of all elements functions such that I can write it in the following form as f divided by g. H is equal to f divided by g, and g of p is non-zero. So usually we will write this in a simpler form. We just write this is the set of all f divided by g in Kx such that g of p is non-zero. But obviously, this just means you can choose a representation like this, such that the denominator is not zero. Not that it's true for all representations. Okay, and if I have an open subset, so we say that f, or maybe I call it, was always called h in Kx is defined at a point P in X. If it lies in the local ring of X at P. So the local ring of X at P is all the rational functions defined at P. And then if you have an open subset, the ring of regular functions on U just the set of all rational functions which are defined at every point in P. That so I denote it by OU, set of all H in Kx such that H is defined at every U. And I can also, if I wish, write this. This is the intersection over all P in U of the local ring of X in P, where the intersection takes place in the field of rational functions on X. So that means that for every point P in U, I can find a representation f divided by g such that g of P is not 0. Obviously, it does not mean that I can find one such representation which works for all possible P's. That's a much stronger condition. So if I have a rational function, it will always be a regular function on some open subset. And there I can find the biggest such open subset, which is called the domain. Definition. So function, the domain of H just the set of all points P in X where it's defined. Defined at P. And you can see that this is a non-empty open subset because we can, so this is non-empty open subset X, because you can write it. No, it just means that for all representations, you take the union over all the union where the denominator is non-zero. So I can write this. This is equal to the union over all X minus the zero set of G, where union is over all polynomials such that I can write H as the class in AX of some polynomial F divided by the class of some polynomial G, of this polynomial G, for some x1 to xn. So it's therefore a union of open subsets. So this precisely describes what I wanted, because this says that it's defined at a point P means precisely that it is not, that the point does not lie in the zero set of G. And so that's what we have here. Okay, I can also say something more about this local ring. So there's a maximal ideal in it, the maximal ideal. So the maximal ideal MP in OXP is just the set of all F divided by G such that H of P is equal to 0. So that H in OXP such that, well, here just write H of P is equal to 0, by which I mean that H can be written as F divided by G such that F of P is 0, G of P different from 0. I wanted to write it like this. And this is an ideal. It is a maximal ideal. Because it's the kernel of the evaluation homomorphism at P, which goes from the local ring at P to K and sends H to H of P, by which I mean F of P divided by G of P. Okay. Now, you can easily check if I take OXP without the maximal ideal, it consists of units. Every element in OXP which is not in a maximal ideal is a unit, and from this it follows that MP of OXP. Or maybe don't have to worry about this too much, but anyway, so in commutative algebra, there's the notion of a local ring. A local ring is a ring which has a unique maximal ideal such that the complement of that ideal of units, and this obviously comes, this definition comes from the local ring of a variety in a point, which has this property. Okay, so now let's go a bit further. I mean, I have already implicitly yeah, I kind of have done it in a slightly incorrect order, but so if I have what I should have said before, but I say it now, so I have defined what the regular functions in open subset are. I just say it should be defined at every point P in U. And the claim is now that every element in the local ring, every regular function on U, indeed gives us a function from U to K. And it's determined by this function. So the regular functions f in OU define functions, call them H from U to K, namely if f is equal to f divided by g, with f and g x, and g of p different from 0, we put h of p. As everybody would expect, f of p divided by g of p. It's an exercise to check that this is well defined. There are obviously many ways, or there can be many ways how to write how to write h as the quotient f divided by g for f and g in AX, and the claim is such that the g of p is non-zero, and then it follows directly from the definition that, however, this value h of p equal to f of p divided by g of p is independent of how I write it. Okay, and so it was so now as a last thing about it, we want to see that if we have a affine variety in this way, and we look at the functions which are regular on the whole of the affine variety, we don't get anything new. We just get the, so we just get, again, AX, or the polynomial function. So a function which is regular on a whole of an affine variety is just element in the coordinate ring, or polynomial function. So x in variety, if I take OX, these are the functions which are regular on the whole of X, just AX. So, I mean, here identified with a set of all f divided by 1 with f. We had viewed Ax was by definition a subring of Kx. So this is precisely, in some sense, opposite of what I said here. For every point P in X, we can find a representation of, so assume we have an element in OX, then for every point in X, we can find a representation, this H is equal to F divided by G, such that G of P is non-zero. And then from this, we should be able to deduce that we can make the denominator everywhere to be just the constant function 1. It's a quite strong statement. And it's not maybe surprising that one needs some big theorem, so we actually use the Nullstellensatz for this. So obviously, we have that Ax is contained in O of X. Now we have to look at the other inclusion. So let H be an element of OX. So that means then for every point in X, we can find, we can write H equal to F divided by G, where these brackets mean the class in AX, and F and G are polynomials, where F and G are polynomials, and G of P is non-zero. In theory, for every point, we might need a different polynomial, different such representation, but anyway, we can do this. So now we look at the following ideal. Set of all polynomials, 1 to xn, are precisely these G which occur here, such that if we take our function H and we multiply it with the class of G, we have taken this rational function, we multiply it with an element in AX, that then indeed it is an element in AX. That means we can, so if we multiply by this, the denominator, this thing has no denominator. So this means these are all G, which we can take as denominators for H in such a representation. Now, we have just seen, first, we have seen this is this formula here, this statement. We have seen that if we take the zero set of J intersected with X, this is the empty set. Because what does it say? For every point P in X, there exists such a G, such that G of P is non-zero. And this says precisely this. On the other hand, J is clearly an ideal. So J here. And J contains the ideal of X. Because if I multiply our H with an element in the ideal of X, I get 0. And so certainly that lies in AX. So the class of an element in the ideal of X is 0, and so I get 0. And so this certainly is contained. So we have that the zero set of J intersected X is empty, but J contains the ideal of X. If you put this together, it follows, so that means that the zero set of J is contained in X. But the intersection with X is empty, so that means the zero set of J is empty. And so we have found an ideal in Kx1 to Xn whose zero set is empty. So by the weak Nullstellensatz, we have that it contains 1. Okay. So 1 is an element in J. But what does it mean? If I multiply H by 1, I am in Ix. So H is in Ix. Okay. So this is it's a simple proof, but we have been using this this rather deep result here to obtain it. So it's not obvious. Okay. Now I want to deal with the quasi-projective case, say what rational functions on quasi-projective varieties are. Regular and rational functions on quasi-projective varieties are. We want to make basically the same definitions, but we have to somehow, as always, replace polynomials by homogeneous polynomials. And then if you take elements in the, take fractions of polynomials, they must be fractions of two homogeneous polynomials of the same degree. So on quasi-projective varieties. So again, definition, basically same story. Let X in Pn be say a projective variety. So then Ex, so and let Ex be its homogeneous ideal. And I can look at the so-called homogeneous coordinate ring, which is just the quotient of k x0 to xn divided by x. So the homogeneous coordinate ring Sx, which is defined to be k xn divided by homogeneous ideal. X is a projective variety, so Ix is a prime ideal, so this is an integral domain. And we can again form its quotient field, so that Q of Sx, fraction field. However, now a rational function on X will not precisely be any element in the fraction field, but I have to be a little bit more careful. So I should maybe also have said before, if I have an element in Sx, this will not define a function from X to K, because you know, if I have a polynomial, so because these are, even these would be equivalence class of polynomials if I replace the coordinates by multiples of it. So multiply every coordinate by lambda. This gives me the same point in projective space, but the value of the polynomial would be different. And so this cannot give us well-defined functions. But if I take the quotient of homogeneous polynomials of the same degree, this will make sense. And so definition. So that F element in Sx, F is called homogeneous of degree D. If it has a representative which is homogeneous of degree. So if F is equal to F for some F in Kx0 to Xn, homogeneous of degree D. Easy to check that this is well defined. So if any homogeneous representative of F will have the same degree. And now I will only look at elements in this fraction field which are quotients of elements which are homogeneous of the same degree. Define well-defined functions. So I will say denote Sx the elements F in X which are and I define the fraction, the field of rational functions just the elements in the fraction field which are quotients of homogeneous polynomials of the same. So this is Kx, defined to be the set of all F divided by G in fraction field of Sx, such that F and G are both in homogeneous part of degree D for some D. In other words, F and G are homogeneous of the same degree. And then you can see that whenever G of P is not equal to 0, so maybe I can, so we'll see in a moment. Okay, so now we can do the same definition as in the affine case. First, we define the local ring. So the local ring of X at P is again the set of all F divided by G in Kx, such that G of P is different from 0. Where here G of P is different from 0 means that, so whether a polynomial is 0 at a point in projective space we can see. And this is just a class of a polynomial, so this makes sense. And so where obviously if F divided by G in Kx means that, so this means by definition, if we write like this, f divided by g in kx, it means that f and g are homogeneous of the same degree. We say, in this case, so this was O xp, and we say that H is defined at P, so H in Kx, where I write it, is defined at P if H is in the local ring of X at P. So that means we can write it as f divided by g, f and g homogeneous of the same degree, with g of p different from 0. And now, in such a point, so in the points where it is defined, it actually defines as a function. So again, what maybe I can first say, obviously we have again m. Well, so for H, which I can write, say, as f divided by g, this again means the class in Sx of some polynomial, where f and g homogeneous of some degree. And P some point in X. So X was in Pn, no? Beginning, but I can repeat it. We put H of P f of A0 to AN divided by G of A0 to AN. One can again check A. These are two polynomials homogeneous of the same degree, and that it is defined, so in X, H defined at P. So I write it like this. So for any f, so P as above with G of P different from 0. So we can just put the coordinates of the point into f and g, and we get our value H of P. And you can again check this is well defined. In this case, there are two things to check. So first, as these are homogeneous of the same degree, if I replace A0 to n by lambda A0 to lambda an, which is the same point in Pn, and the same here, so then we get lambda to the d comes out here, lambda to the d comes out here, so we get the same result. And also, if you take another other representatives of the same H, we will get the same result. This one can check. And so we can therefore associate to any point P H of P, which is just by doing this. So we also call MP in OXP is again the maximal ideal, where MP obviously is defined analogously to V4. This is the set of all H in OXP, such that h of p is equal to 0. Again, this is a maximal ideal, and the complement of this maximal ideal contains only of units. And so again, OXP will be a local ring. Okay. And finally, you can, as in the affine case, define regular functions on open sets. Functions. So for U in open, the ring of regular functions on U is just, so again denoted by OU. This is the set of all H X such that H is defined at P. And is, as in the affine case, an H in OU defines us a function from U to K. If H is an element OU, then the function, which are also H from U to K, which sends P, H of P, as I have defined there, is a well-defined function. So any regular function actually does define us on an open subset, does define us a function from U to K. And we have again, say, the domain of a rational function. No? So domain of a rational function the H Kx is again is the non-empty open subset. Domain of H, which is defined to be the set of all P and X, so that H is defined at P. And this is an open subset in X. And the fact that this is an open subset and non-empty, the proof is the same as in the affine case, which we did a few minutes ago. Okay, so I have defined for you, both in the affine and in the projective case, what a rational function is and what a regular function on an open subset is. And I have shown you that such a regular function on open subset actually defines your function from that open subset to K. So that somehow justifies the name. But obviously, we would also want to really see that we can identify this subset of Kx with a set of function from U to K. So we want that this function here defines us the element H in OU. And it's not just that we want to briefly see. And also we want to see, describe in a different way what these functions are that we obtain in this way. So this is the following proposition. So now we are either in the affine or net X. Affine projective variety. And let U subset X be an open subset. Say maybe non-empty, but anyway. So non-empty. First, so we find the map from OU inside Kx to functions from U to K, which sends an element F here. So, I mean, I just denoted for now as F restricted to U, but it's just what I had defined here. So this is just a function from U to K, which sends a point P to F of P. So this map is injective. And furthermore, the image has an explicit description. The image is the set of functions f k, which are locally given by quotients of polynomials. So such that every point P U has a neighborhood, has an open neighborhood. I'll just always write neighborhood for open neighborhood. Neighborhood B or such that they exist polynomials so there I have to distinguish between the affine and projective case, namely either we have F and G in K x1 to xn in the affine case, or F and G are homogeneous of the same degree. In Kx1 to xn plus 1, x0 to xn, such that we can write in this open neighborhood the function as a quotient of these two polynomials. With f of q, large f of q, all q in B. Okay. So every point has a neighborhood such that the function is given as a quotient of these polynomials. So by this, maybe I should say, to be completely on the safe side, that you're not confused, just write f a0 n, but this is precisely the problem, so I'll leave it. So here, obviously, in the projective case, it means I take any representative of Q, I take the same representative of the same Q here and take the quotient. All Q. Okay. And the second statement is a trivial consequence. So that f and g regular functions on U, let V subset U be an open subset if f restricted to V is equal to G, then f is equal to G. So both as elements in OU, but also on functions on U. So there's this certain rational functions have this rigidity that they're determined by their value on any, regardless how small, open subset. If you know it on any open subset, you know it everywhere where it's defined. Okay, so let me try to sketch the proof. So I want to just see that I can recover this rational function here, f in OU, from this map. So we know that this map, which I have defined here, f goes to f restricted to U, U like this, the ring homomorphism. Now if you take the sum of the two functions in Kx, it gives you the sum here and so on. So thus, in order to see that it's injective, it's enough to see that the kernel is 0. So thus, that f be an element in OU such that f restricted to U is the 0 map. So no, this is here, this map. And we have to show that f is actually 0 as an element in Kx. So for P, so we take some point P in U, then we can write this f as, say, divided by H, where G and H are polynomials, either homogeneous of the same degree, or so xn or gh in k x0 to xn homogeneous of the same degree. And it's supposed to be defined on U, and so we can do it in such a way that h of p is different from 0. Yeah, maybe I did it in a slightly confused way. Maybe first, maybe this in a moment. I first want to show that the second statement, that the image is these here, these is given by the quotients of polynomials. So then obviously I can use this representation f equal to g divided by h wherever h is non-zero. So then on the open neighborhood, out z of g, we have f of q h of q for all q. So this is this second statement that for every point, it has every point P in U has a neighborhood such that such polynomials exist, and we can write it in this form. So this was one statement. Now, if this f restricted to U 0, then obviously f restricted to V 0. So we have that f of q, h of q, g of q, divided by h of q, 0 for all q open subset in X and non-empty. And h of q is non-zero, so that it follows that g of q is 0 for all q in V. And so, but as V is a non-empty open subset of X, it follows that G vanishes on the whole of X. Because if a polynomial vanishes on an open subset, the open subset is dense, and so it has to vanish on the whole of X. And so but that means the class of G in AX is 0. So thus, F, which is divided by H, is just 0 in Kx and thus in O of U. Okay, so this shows this part 1, and the second part is trivial. So V should be a non-empty open subset, because obviously if F and G are in OU, they also, and we have an open subset, they also are in OV. And if they are in OV, they define the same function. So therefore, on V they define the same function. So they are the same elements of OV, but OV is just a subset of Kx. So they define the same element in Kx, and so they define the same element in OU. Okay, anyway, you can check it, but this is 2, 1 to 2 follows definitions. If it's not clear to you, maybe you should go through it. Okay. So in other words, so such a rational function, such a regular function, which by itself is just the quotients of elements in AX, is giving such a function is the same as giving a function on an open subset which is locally given by quotients of polynomials. And I can always make the open subset smaller, but the function is still uniquely determined by what it does on any open subset, on any non-empty open subset. Okay, so that's maybe just and so in future, obviously, we have just seen that this map, which sends an element here to the actual function, is injective. So we will identify OU with the image so that we can view OU actually as set of functions. OU. F in OU. That called F restricted to U. Just a small corollary. Say function f from U A is regular on U, if and only if every point has a neighborhood such that it's regular there. U has a neighborhood such that I take this neighborhood I call V such that F restricted to V is. This follows directly from the second description because it just says, so to be in OU or in OV means that it's locally, so that every point has a neighborhood such that it's locally given as a quotient of two polynomials, and that's already in this form. And so it's clear that, that this follows. I want to give a few more properties of regular functions, which are useful to work with them. So, one of them is that they form a ring or a K algebra, that the inverse of that if you have a function which is regular and has no zeros on some open subset, then its inverse is also regular, and that a regular function is continuous if you give K the Zariski topology. So the first is this remark. Let X be a variety. That means X can be quasi-affine or quasi-projective. And I take an open subset. Then first, O of U is a K algebra. So it's a ring, and it contains the constants as a subring, and it means you can, in particular, you can form, can put an element in AU into any polynomial. You can put elements in, you replace the coordinates in a polynomial by elements in OU, and you get an element in OU. So, in particular, so if we have a polynomial in variables, and I have some elements in OU, then G of F1 to Fn is also in OU. And this is clear because we see that if I have two elements in OU, then their sum lies there, the product lies there, and a constant function also is in OU. And so any polynomial, and so we can just take sums and products and multiply by constants. So in this way, we get any polynomial in the Fi, and this will also lie in OU. So this goes directly, and then if I have an element, if F is regular on U and has no zero on U, then 1 over F is also in U. And that's basically, follows basically from the definition. So we can write, so F is certainly an element X without 0, if it does this. And so then therefore 1 over F is also an element in Kx without 0. We just have to see that it's regular for all P in U. So for all U, we can write F equal to G divided by H, where these are elements in AX or in SX of the same degree, with so H of P different from 0. That's because it's defined there, and it's also supposed to be non-zero, so also, and G of P. That's precisely the definition of this thing being regular on U. But then obviously thus 1 over F, which is H divided by G, also regular at all P in U. Directly from the definition. And then I also wanted to claim that regular functions are continuous. Then I'm done with these regular functions for now, I think. So let X in the N or X in Pn subvariety. And let U open and F regular on U. Then I claim F as a function from U to K is continuous. So obviously, if one wants to make such a statement, I have to use the Zariski topology on K. So I view K as A1 and give it the Zariski topology. Okay, and so in this form, it's relatively easy. So we can write so obviously a function is continuous if it's continuous in the neighborhood of every point. So therefore, we know that every point has a neighborhood so that we can write F as a quotient of two polynomials. So we can as well assume that F is a quotient of polynomials. So proof, we can assume that F is equal to G divided by H, where G and H are polynomials, either, I just write me polynomials, either homogeneous of the same degree in the projective case or just polynomials, and H does not vanish on you. H has no zero. Now we can, otherwise we have the neighborhood of any given point. So otherwise for any point we find such a representation such that H of P is non-zero, then on this corresponding, on the complement of the zero set of H, we can write it like this. And then, okay, so to say that this map is continuous is not such a big deal because the Zariski topology is like that. We know that the closed subsets in the Zariski topology are just A1, the empty set, and the finite sets. So obviously the inverse image of the empty set is the empty set, which is open. The inverse image of A1 is U, which is also open. And so we only have to see that the inverse image of any point. But I didn't want it open. I want the inverse image of any closed subset is closed. So the inverse image of the empty set is closed because the empty set, the inverse image of A1 is the whole of U, which is closed in U. So we only have to see that the inverse image of a point in A1 is closed. And so that A be a point 1, then what is f to the minus 1 A? Set of all Q in U such that divided by H of Q A, which I can also write, it's a set of all Q in U such that G of Q minus A times H of Q 0. So this is equal to U intersected zero set of the polynomial G minus A times H. G minus A times H is a polynomial, and it's also in the affine case that's finite. In the projective case, these two are homogeneous of the same degree, and A is just a constant in K. So this is a homogeneous polynomial. And so I can look at the zero set. So this is closed in U. So the map is continuous. Okay. Was this part. And now I've made all this big story about these functions, and the reason is that I want to define what a morphism is in terms of regular functions. So we had these polynomial maps for affine algebraic sets, which were just that coordinate-wise it's given by polynomials, but in general one cannot define morphisms, so allowed maps between varieties like that, but one has to allow something slightly more complicated, and so for this we need these regular functions. So the definition I want to use is that a morphism between two varieties is a map which is, for one thing, between these varieties, which is continuous, and it preserves regular functions. So that means if you have a regular function, you can pull it back. So we take you compose it with a map. You can pull it back to the source, and then you want to have that it is also a regular function. So let me do this property. properly. Definition. Maybe I call this, so these are morphisms. X and Y definition. X and Y be varieties. They're allowed to be, can be, I mean, quasi-affine or quasi-projective. Maybe one of them quasi-affine, the other quasi-projective, or both of them either affine or projective or something like that. So, but any varieties, a morphism phi from X to Y is a continuous map phi from X to Y such that if I have an open subset, so for every open subset U in the target, and any regular function on this open subset we have that the pullback, so I call this phi star f, which is just defined to be the composition f composed with phi. So the composition obviously now is a map from phi to the -1 of u to k, and this one we want to be regular on phi to the -1 of u. So we only are able to talk about regular functions on open subsets. Now, as we require the map to be continuous, the phi is continuous, so the inverse image phi to the -1 of u is also open, so we can talk about regular functions on this open subset, and we require that the pullback, that is this composition, is regular on the inverse image. Okay, so this is the definition. It's a little bit abstract, and we should also, but we will see that one can also describe it more concretely, but it has the advantage to have one short definition which covers all the cases at once. And it also generalizes nicely to if one looks at more general things like schemes and so on. So obviously this star, so the homomorphism star from OU O -1 of U is called the pullback by phi. So it's clear that this composition is a homomorphism. If you take the product of two functions, it pulls back to the composition will be the product of the pullbacks, and if you take the sum, it will be the sum. So it's even a homomorphism, say, of K algebras, because obviously constant functions get also pulled back to constant functions. So it's clear from this definition that you can define the composition of morphisms, and this will be a morphism. Of morphisms. Morphism. No, so if x, so maybe phi x to y, y to z are morphisms, then psi composed with phi from x to z is also morphism. This is basically trivial because first, the composition of psi and phi is continuous as a composition of continuous maps. That's fine. And if U, so if U subset Z is open, F is regular on U, then I have first, as psi is a morphism, we get psi star F is regular on psi to the -1 of U. And then as phi is also a morphism, it follows that phi star psi star F is regular on is it phi to the -1 of psi to the -1 of U. And clearly this is just psi composed with phi, the pullback of F, and this is just the inverse image of U under psi composed with phi. Okay, so basically, trivially from the definition, the composition of morphisms is a morphism. And a morphism will be called an isomorphism if it has two-sided inverse. So Y isomorphism morphism phi from X such that psi composed with phi is equal to the X and phi composed with psi. As usual. Okay. Maybe as a last thing, I want to see that you can give morphisms locally. So if you have a map, P from X to Y, for it to be a morphism, it's enough, it's a morphism in a neighborhood of every point. It's, again, quite simple, but one will want to use it often, or sometimes. So a map X to Y between varieties is a morphism and only if every P in X neighborhood P such that P restricted to V from V to Y is a morphism. Again, this is quite easy because being continuous is a local property. So that phi from X to Y, any map between topological spaces is continuous if and only if every point in the source has a neighborhood, so that if I restrict my map to this neighborhood, it's continuous. Now this follows directly from the definitions. And for the pullback, it's basically the same. So if U subset Y is open, F is in U, then if I have this neighborhood here, so I get that if I take phi star F, restrict it to V intersected to phi, so I assume this statement here, no? So I do this. So if I have that phi restricted to V morphism, then this, so maybe I can a little bit more. So assume statement, so every P in X has a neighborhood X such that morphism. We've seen, then it follows that P is continuous, because that's completely standard. And now, so if I take any open subset U in X, in Y, and F is a regular function on U, then I have to see that the pullback is regular on the inverse image. But then for every point P, I have this neighborhood, maybe I call it P. Then if I take phi star, if I take the pullback of F and I restrict it to Vp intersected phi to the minus 1 of U, this is the same as the pullback of F via this map from phi restricted to V to Y. This is regular on this open subset. Because phi restricted to Vp is morphism. And so that means this function is regular on all these open subsets, and these open subsets cover phi to the minus 1 of U, because the Vp are, for every point P, we have a neighborhood where this holds. So we had just seen that being regular is a local property, so therefore it follows that phi star F regular on phi to the minus 1 of U. Because it's regular on Vp intersected phi to the minus 1 of U for all the Vp, every neighborhood of every point. And to be regular on an open subset, it's enough to be regular in the neighborhood of every point in this open subset. Okay. See? Yeah, okay, so maybe I will stop here. So next, I will show more concretely that, so if I have a morphism to, say, an affine variety or subvariety of AN, its coordinates are given by regular functions. Like we had before, that polynomial functions were given by polynomials, but here it's by regular functions. And we also will show a similar statement for projective, for morphisms to projective varieties. And then we will look at some examples. Okay, so thank you very much. Are there questions? Okay. Comments? Okay, so then I wish you a good. So if there's anything which is not clear, maybe you can't ask immediately, but then you would maybe you, if it's not clear to me, please ask me at the beginning of the next lecture. Okay, so otherwise I wish you a good afternoon, and we see each other already tomorrow. So, okay.
Okay.
Bye.
Thank you.
Mm-hmm.